this video, we will be looking at a specific vector application, which is velocity. Now, before we do that, just a quick recap of a vector versus a scalar quantity. A vector quantity has a magnitude and direction, whereas a scalar quantity has magnitude only. So in terms of velocity, velocity is a vector because it includes a direction. For example, if I said I am driving 100 kilometers per hour north, that is a velocity. If I just say I am driving 100 kilometers per hour, that is a scalar quantity, and that is speed. Now, velocity is a quantity that can be described as the motion of an object, but all motion is relative. So any reference frame can be chosen to be at rest while the others are relative to it. For example, if I am standing still and I see a car driving by, the speed of that car relative to me not moving, would be, let's say, 100 kilometers per hour if that's what they're driving. However, if I'm also moving, so I'm in a car and there's another car beside me, now when I look at that car, their velocity will look less because I am moving as well, if we're going in the same direction, for example. So that is relative velocity when you're talking about the velocity of one object with respect to another. Okay? So a specific example might be something with a boat and an airplane, let's say. If you want to know the velocity of an airplane, like what it's actually flying at, we have two velocities that we need to consider. The velocity of the plane relative to the air, and the velocity of the air relative to the ground. Think about when you're on an airplane and let's say you're going to Europe. When you go to Europe, you might have a certain flight time. On the way back, the flight time won't be the same. It's either going to be more or less depending on the direction of the airstream. Like, is it helping the plane go faster, or is it slowing it down a little bit so it takes you even longer to get home? And it's the same idea with being on a boat. We have the water current that might help push the boat go faster, or it might stop it a little bit and slow it down. So if I wanted to find the velocity of the airplane, I would be adding the velocity of the plane relative to the air, and then the velocity of the air relative to the ground. And when we add those, we get the velocity of the plane relative to the ground. So for the person who's at rest at ground level, how they would see the plane flying. So let's start with some examples where the directions aren't too crazy. Two F1 drivers are driving at the same speed of 355 kilometers per hour down a straight going towards the west. If you are a spectator in the stands, what is the car's velocity relative to you? And what about the velocity relative to each other? So let's say this is you, the spectator. I have one car going to the west, 355 kilometers per hour, and I have another car, exact same speed. For me, who's standing still, when I see the cars, I see them going at a velocity of 355 kilometers per hour. But for the F1 driver who's in the car, when they look at the other car, if they're going in the exact same direction, their speeds relative to each other, it's going to be 0 kilometers per hour because they're lined up, they're going in the exact same direction, the exact same speed. So when we have, let's say, the velocity of one object relative to the other, the way we would calculate that is by subtracting the velocity of the second object minus the velocity of the first object. So when I was trying to find the velocity of the car relative to me, I would be doing the velocity of the car minus my velocity, which was 0. So 355 minus 0 was 355. Whereas when I was trying to find the velocity of the first car relative to the second car, when I subtract 355 minus 355, because they have the same speeds, I got 0 kilometers per hour. Let's try another one. A person walks inside a subway car at a velocity of 4 kilometers per hour towards the front of the train, relative to the subway car. If the subway is traveling at 60 kilometers per hour relative to the ground, what is the person's velocity relative to the ground? So here are the two speeds that are given to us. They're not relative to the same thing. One is relative to the subway car, the other is relative to the ground. So the velocity of the person relative to the subway car is 4 kilometers per hour, and the velocity of the subway car relative to the ground is 60 kilometers per hour. So here's the person going 4 kilometers per hour, and here's the subway car going 60 kilometers per hour, and they're going in the same direction. So if I want to find the velocity of the person relative to the ground, I need to add these two vectors, the velocity of the person relative to the subway car, and then the velocity of the subway car relative to the ground. And that would give me 64 kilometers per hour. So if I was standing on the edge looking at the subway car, it's going 60, the person's going 4. Together, I would see the person walking 64 kilometers per hour because those two velocities are added together. But what if the person was going in the other direction? So based on the scenario above, what is the person's velocity relative to the ground if he turns around and walks towards the back of the subway? So now we still have the subway going 60 kilometers per hour, but now we have the person going in the other direction, 4 kilometers per hour. Our resultant velocity is this. It's still going to look like the person's walking forward. It's still going in the same direction as the subway, but it's going to look a little slower because going in the opposite direction counteracts the forwards from the subway. So now the velocity of the person relative to the ground is going to be 56 kilometers per hour because we're subtracting the 4 because it's going in the other direction. So these first three examples that we looked at are all very linear because the objects were going in the same direction, different speeds, but relatively parallel directions, let's say. Let's get a little fancier though. An airplane heading due north at 500 kilometers per hour encounters a wind of 150 kilometers from north 60 degrees east. Determine the resultant ground velocity of the plane. So if I want the velocity of the plane relative to the ground, I have to add the velocity of the plane relative to the air with the velocity of the air relative to the ground. In other words, the airplane's velocity relative to the air with the wind. So let's start off with a diagram. I'm going to start with a little compass here. And the airplane is going north. It's going north 500 kilometers per hour. Then it encounters a wind from north 60 east. It's not going towards northeast. It's coming from north 60 east. So north 60 east is this. It's coming from that direction. So this is the wind's vector. 150 kilometers per hour. Then using our knowledge of opposite angles, if you have two lines intersecting, the angles opposite each other must match. So this must also be 60. And now we can draw in our resultant vector. This is the velocity of the plane relative to the ground. I'm just going to call it r for the resultant. If I calculate the length of that side, I'll have the magnitude. And if I calculate this angle here, that will be my direction with reference to north. So it's going to be something northwest. So to calculate the magnitude, I'm going to use my cosine law. As a reminder, here is your cosine law. But because I know I need to get rid of that exponent at some point, I'm just going to go straight to square rooting. So the magnitude of the resultant vector will be 500 squared plus 150 squared minus double those two sides and then times cos of that contained angle. That's the reason we're doing cosine law. We have two sides and the contained angle. And now we can punch it into our calculator and we get 444.4 kilometers per hour. And now let's do a sine law because now we have a full pair if we know that this is 444 kilometers per hour. So we have a full pair between the 60 degrees and that resultant. And we want theta, 150 is across from it. And then we can cross multiply from here. I'll divide both sides by that 444.4. And then of course, because I'm solving for an angle, I will take the sine inverse of that fraction. And when I do, I get 17 degrees. And that 17 degrees is right along that north line because the plane was heading in the north direction. So that's going to be north 17 degrees towards the west. So therefore, the plane's velocity is 444.4 kilometers per hour, north 17 degrees west. And if I wanted a true bearing, I could do 360 minus 17, so 343 degrees, and I could use that as well since it didn't specify what kind of bearing to give. However, if you are given a quadrant bearing, your answer should also be using the same type of bearing. All right, final example here. A river is 2 kilometers wide and flows at 6 kilometers per hour towards the south. Anna is driving a motorboat which has a speed of 20 kilometers per hour in still water. She heads out from one end of the bank in a direction perpendicular to the current. A marina lies directly across the river from the starting point on the opposite bank. All right, so here's my river bank, let's say, and it is 2 kilometers wide across. And there is a current going towards the south. I'm not going to put that in my same diagram that I've already started because this one is going to be about distance and I'll do one about velocity. So I have another triangle. Here's the current, 6 kilometers per hour to the south. Anna is driving a motorboat and its speed is 20 kilometers per hour and she decides to head out in a direction perpendicular to the current. So this is Anna's velocity vector. So she's going towards the east. Or she could also be going towards the west depending on what side of this river she's on. But I've just put her right here. Here's Anna, here's the marina. So Anna and marina. Now the first question is, how far downstream from marina will the current push the boat? So if this is Anna's boat velocity and this is the current's velocity, what she actually ends up traveling is this resultant vector. So she's going to get pushed down. Now I am looking for a distance, so I have to use this diagram here. She's going to get pushed a certain amount based on how her boat gets pushed further down. So our goal is to solve for this distance. Now, I don't have any information in this triangle. However, these two triangles here are similar triangles. The reason being, all their angles are the same. So this angle here, it's a 90-degree angle for both because the river is 2 kilometers wide and that distance is perpendicular to that river bank. And here we were told and as traveling perpendicular to the current. So we know both of these are 90. And this angle here and this angle here, they both represent the direction Anna's actually traveling in, so they must match. And then automatically the third angle has to be the same. The minute you have two triangles that have the same angles, they are similar, which means the relationship or the ratio of the corresponding sides, so 20 to 2, has to be the same as the ratio of 6 to that side D. Now I can see here that to get from 2 to 20, I can just multiply by 10, or take 20 and divide it by 10 to get to 2, which means I can do the same thing here. I can take 6, divide it by 10 to get my distance. I can see that visually. Another way to set it up is with some proportions. So the relationship between 20 and 2 has to be the same as the relationship between 6 and D. And then you can cross multiply. 20D equals 12. And when you divide both sides by 20, you get that same 0.6 kilometers. So therefore, Anna is pushed 0.6 kilometers downstream from that marina. Next, we want to see how long it's going to take for the boat to cross the river. Well, if we're talking about time, I'm thinking about that speed formula. Speed is equal to the distance divided by the time. If you know this, you can always manipulate this formula, and time is equivalent to distance divided by speed. So if I could figure out the distance that she actually travels, I'll label that x, and I could figure out her speed here, which is the resultant vector, I can divide those, and then I'll have the time. And in each of these triangles, I have two side lengths, so I can do a Pythagorean theorem, or the minute I find one of the side lengths, I can use the similar triangles to find the hypotenuse of the other. I'm just going to do a Pythagorean theorem twice. So to solve for x, x squared is equal to 2 squared plus 0.6 squared. And I know I'm going to square root both sides. I could have done that from the very beginning, and I'll punch that into my calculator all in one go, and I get 2.1 kilometers. So that's how much she actually travels. Now, her resultant vector, the magnitude, I'm going to go straight to square rooting, 20 squared plus 6 squared, and I get approximately 20.9 kilometers per hour. Now that I have my distance and I have my speed, I can calculate the time by dividing the two. And when you do that, you get 0.100 hours. If I want to convert this into minutes, I'll just multiply it by 60 to get approximately 6 minutes. So that's how long it would take her to cross the river. Therefore, it will take Anna 6 minutes. But what if she doesn't want to get pushed down the stream? If Anna decides that she wants to end up directly across the river at the marina, in what direction should she head, and what is the resultant velocity of the boat? So what if she wants to do this? That's the path she wants, but there's still a current that's pushing her south. So this is what she would have to do. This would have to be her 20 kilometers per hour. The current pushes her down so that her resultant vector is perpendicular to that riverbank, and she ends up directly across to the marina. So we need to know the magnitude, and we need to know this angle to see what direction she should head in. And this is just a nice right triangle because we know these are perpendicular, so I can use my SOHCAHTOA and my Pythagorean theorem knowledge. So my resultant vector squared plus 6 squared will equal the hypotenuse squared, which means the resultant will be the 20 squared minus the 6 squared, all square rooted. And that is going to give us approximately 19.1 kilometers per hour. So that's what her boat will actually travel at because of that current pushing her. And then for our angle, that angle 6 is opposite, 20 is the hypotenuse, so I'll just use sine. And I'll take a sine inverse and I get approximately 17 degrees. So I'm going to write, therefore, Anna should head. And in terms of her direction, we're 17 degrees from the resultant vector, but if this is the riverbank, this is her angle with regards to that riverbank. So 90 minus 17, 73 degrees. So she should head 73 degrees away from the riverbank. And the way I've drawn it, this would look like north 73 degrees east because I placed her to the west of the marina. And the resultant velocity will be 19.1 kilometers per hour. And that's it. So the trick to these questions is having really nice, clear diagrams, and we are just relying on our sine law, cosine law, SOHCAHTOA, and Pythagorean theorem knowledge.